So I was saying to kids before I started recording that this calculation isn't asked for. The formula for this I don't remember because they don't ask it, and I just double checked. It's not in the list of formulas on a real test, which means they can't ask you to calculate. They calculate it. They give formulas in the official test formula reference pages that are so elementary that I was really surprised. There's stuff in there. I mean, I can't even remember. But for instance, they define pH, which I guess they would, but they go really down. So if it's not there, they can't ask it. All we should really be learning in the end, because we've got so much to learn, is that the absorbances do change with the same proportions that the molarities do, and therefore you can use the change in absorbances in the integrated rate law. And you can say that the absorbance went up by a factor of 3.5, therefore the molarity went up by a factor of 3.5. And in fact, on B, they ask for, what is it? The rate constant. So we're going to use the first order integrated rate law because it is a first order decomposition. And we're going to use figures from the absorbance column, and it's going to work. And I was saying when we were in person that it doesn't matter where you start and stop, really, because, I mean, this could have been 0.8, right? It could have been 1.3892, right? But it doesn't matter where you start and stop because the changes keep working by the same proportion per second or per minute. So pick a start, pick a stop. If you want to pick this is the start at time 0, this is the start, this is the stop, fine. Now, you could even do this and call this time 0. You just need then to make sure that if you're going to pick this as the start, that it's your time elapsed. And so you need to take the time differential between here, which is what, 9.2? 9.2 minutes. So then this would say 9.2 minutes. Remember, it's the time elapsed, but they went from here to here. So this is the starting molarity. Sorry, this is the starting molarity. The one with the 0 at time 0. And this is the ending molarity. Excuse me, it's absorbance. That's the whole point. We're using the absorbance, right? I've said molarity so many times, I just did it again. Starting absorbance, ending absorbance. You do get a calculator. As Chris pointed out, you can also reduce this to ln of 0.2 over 0.6, which is ln of 1/3. In case you consider that a shortcut. I guess it's sort of a shortcut. And then you do get a negative number because you're taking natural log of a number between 0 and 1. So you get a negative number equals negative k, which is how we get a positive final answer for k. Calculate the number of minutes it takes for the absorbance to drop from 0.6 to 0.075. So we're going to take this as, whoops, I'm off the page. We're going to take this as times 0, right? And then we're going to fill in this right here, 0.075. So we know k because we found it here. So now we can use the first order integrated rate law. And this is the ending time, this is the ending absorbance amount. And we know k, and we're just solving for t. So you can take ln of this over that if you like. And then we divide by that, and you've got t. The other thing would be that when you take these amounts, and technically they do have units if you want to be a little more picky. And when we use molarities, obviously they have units. When you take the natural log of those numbers, though, the units strip out. So you just get a number. And then, so we would get a number. I'm just going to put 2. And then it would be over. I know obviously it's not this minus that is not 2, but something over Well, it's going to be a negative number, isn't it, too, also? 0.0314, right? But here's my point. This is per minute. And when you divide by something that has units in the bottom, the units end up on the top, which is how we have minutes, straight up minutes, not per minute, as the final answer. Because what are we looking for? Not a rate. We're looking for the number of minutes. And the unit for time, we're solving for time. The unit for time should be something that makes sense. Time is just something like minutes, period, not per minute or minute per mole or something weird. In D, they do tell you half-life is natural log of 2 over K. I personally have trouble remembering that, and honestly, I probably end up flipping to the front page, the front section of the test to get the formula, because they ask it so little that I don't remember. But it is there. And we already know K, so all it is just divide. See this. This is a version of that, where I moved this part over to the right. I added it over to the right. And then we have y equals mx plus b. I have seen this recently on one of the more recent tests, that this then can be used as the formula for a straight line. And of course it can, if you think about it. Look what it does. It gives a straight line, right? And my point is that they asked something like, calculate the slope. And I thought, really, they went there. What they're saying is, do you understand that this can be rewritten as this? And since T is not something you get to just, is not particular to the reaction, right? T is something you chose, right? T is not inherent in the reaction, but K is inherent in the reaction as a slope is inherent in a line. So if you can find K, the slope will be negative value of K. So when they ask for the slope, they are asking for K, but make it negative, remember. And take the negative of your answer for the slope. Because look, the slope is negative, right, on a first order? Okay, questions about this part to repeat before Chris maybe? And I see in the chat that he says, I thought you said skip E. Yeah, kind of. You know what? I would concentrate much more on this. This is something to actually think of. Also, to remember, if they give you the straight line graphs, what is this one? Well, down, and I need a mnemonic for this. I don't have one. Down is a first order, and the axes are ln of A versus T. And second order is 1 over A versus T, and it goes up. And I don't have a trick about the up and down part yet. Somebody tell me one sometime. My main point is they could ask this, and that a standard question would be to relate the graph of a first order reaction, and they would want ln of A. Okay, they are right using the Arrhenius equation. There's the one for the Arrhenius equation, which they don't ask, so that's why I'm getting a little dismissive about it. There. That gives that. Eliminate the intermediates. This is produced and yet destroyed. Ding, ding. And let's see. Oh, that's it, isn't it? One of these. Whoop, whoop. That is not quite it. That is not quite it. There is something that is a reactant and yet a product. How is that? Because it is the catalyst. And I would put note to self or something, or circle stuff. The catalyst is a reactant supplied by you or nature. Anyway, it was supplied at the beginning before the reaction started, and yet it is a product. So it is not consumed in the reaction. It is not changed, therefore it is a catalyst, which is why it does not appear in the overall reaction and probably should be put on the top of the arrow, as I was saying some previous day. They don't ask that, but I have definitely seen catalyst written on top of the arrow. I mean, not in the test, but in class, in college class. It is consumed and regenerated. It doesn't have to be consumed and regenerated, by the way. It has to be supplied and yet remain. Whether it was consumed or not is not really the point. It could be, but many catalysts are not really consumed because they are, say, lumps of metal and so forth. And what they do is they provide some sort of landing spot that lowers the activation energy, but they aren't consumed and then regenerated. So that part is not the point, but it could also be the case like it is here. The intermediate is the thing that is created then consumed, so it appears neither on the beginning or the end. The overall reaction would be the addition of the exponents in. Look at the rate law and add the exponents up. This also is a bit memorize it too much for me. Notice this is from 2002, and the test not only changed then, it probably changed twice since then. But if it's going to be second order, what you're going to get is molarity times molarity, right? This is a good question to know. I'm just saying they wouldn't ask it like this as just a straight memorization question. We can figure it out. Let's pretend that they asked it. You can figure it out because the molarities are going to be multiplied by each other, and you're going to get molarity squared times something, and the units for the rate need to be molarity per time, in this case, seconds. So what unit is in the box to change this into that? And it's 1 over molarity second.
Yeah.
That looks like a capital S, I guess. Or, I know I said this at some point, the K needs to have not only molarity in the bottom, but you need to cancel out all but one of the molarities that multiplied in the rate law. So if this is going to be a squared, you're going to need 1. If this is a 4, you're going to need 3. If this is a 5, you're going to need 4 down there. So determine the following, the rate determining step. Well, there are only 2 choices, right? I mean, there are only 2 choices. If this is the rate determining step and it's first, then, right? This is the slow step. Then the rate law should be O3 to the first time. Here, let's look at this. O3 to the first times O single to the first. That's you know what? I just noticed something. It has been a long time since I looked at this. They have the catalyst in the rate law. Oh, I just looked it up and I learned something. If the catalyst is in the rate determining step that's first, it can be in the rate law. So the rate law included the catalyst, which proves that this is the rate determining step 2 ways. Even if it's not the catalyst, this rate law is consistent with the idea that the slow step was the first step. The rate law then is this to the first times that to the first. And the second step is the fast step and can be disregarded for the rate law. Just right there, you get it. Plus also the catalyst can be in the rate law if it's in the first step, and that's the rate determining step. So since it's in the rate law, that also tells you that the first step is the rate determining step. I don't think that let's say this is a free response question. I don't think you're going to get credit for A and B are reactants, C and D are products. They're going to say a duh.
So wait, how do you know it's 3 times? One
Well,
makes use of 3 times faster.
Okay, to be fair, yes, I know they would have to give you demarcations, right?
Right.
But let's say they have demarcations, and maybe someday I'll go in there and build them in. Oh, how do you know 3 times? Reese says, yeah, right. Well, if this is 1, then that's 2, and that's okay. It's supposed to be 3 because I said so. That's not 3. All right. It's close. Can we pretend? I feel like teaching the point right now instead of arguing about whether this is 3 times. But they could ask something like if especially if they nail down the numbers and you can say, oh, this is increasing at 3 times the rate of this, right?
Yeah.
Then they could ask things about, if you got 0.2 of this, how much did you get of that? And the answer is 0.6, stuff like that, right? Like in a related experiment using the same reaction, the student got 0.2 instead of 0.1. So then what is D? Well, it's 0.6. And my point here really is that they could ask something like a multiple choice question. Which of the following formulas could be the true formula for reaction which followed this graph? So from the graph, what happened? And they give 4 different choices, right? Well, again, if we pretend this is 3 times as much as B, right? I had 3 times as much as A, and yet A fell to 0 at basically the same time, right? B fell to 0 at basically the same time as A. So A was reducing at 3 times the rate overall.
Yeah.
So in this reaction, the way I've written it, so then A will run at 3 times the rate of B. For every 3 A's, you use 1 B. And then they'll hit, then they hit 0 together. Now, then some kid says, but what if you don't use 3 times as much? Okay, you're right. But since the graph says we have 3 times as much and then they hit 0 together, then it must be running at 3 A's for every 1 B. That's what you're supposed to get from this. Not that you have to have in the beaker 3 A's for every 1 B. I admit, just because the reaction has this proportion doesn't mean you have in the beaker 3 times as much. But they set it up this way so that it wasn't a nightmare to read. In this case, you had 3 times as much, and then you ran it, and they hit 0 at the same time. So this is using them up at a ratio of 3 to 1. Then, didn't these hit their final molarities at basically the same time? Can we pretend they're the same time?
Yeah.
So then D is made at 3 times the rate of C. Like stoichiometry, I'm going to say when you go from this to that where you're headed is on top, or to say it another way, what you have has the units that you want to cancel out. Therefore, the O2 is on the bottom. Either way you look at it, you end up with this fraction using the coefficients here as the ratios. The O2s cancel out, and you end up with this. 2/3 of 6 is 4. This, x multiplied by 4, y multiplied by a half to get that?
Yeah.
So this grew by a factor of 4, and it is to the first power. This grew by a factor of 5, and it is to the first power. And they are yet multiplied together. So we get 2. So the rate, new rate, is By what factor is 2 times greater?
Yeah, that's what I got.
And I see on my old test from 2017 that I had, and what are the units in K? And you know what? It's a decent question. And we just talked about it. What are the units in K? And I know there's so much. I know. It's the third least passed test in the whole AP system. There's a lot to it. Please study. Please ask me questions. On the other hand, we just talked about it. Let me get through this point, I think.
All right.
What will be the units in K? K will be some number. This is molarity times molarity. And we said K units will have the units of one fewer molarity than these multiplied together. So the K units will be some number times 1 over molarity seconds, or time, and that could be minutes. But so that when we get molarity squared here, times that, we get this one canceling out one of these, and we get molarity per second as the unit for rate. And I'm making that point because they very much get to ask you to calculate K freehand. And if you don't have the unit, it's wrong. It's just wrong. So I'm not, ashamed of hitting this twice or 3 times, because if you get the units wrong, you're wrong, period. But I went through all these steps and I got the right number. It's too bad. The unit is wrong, therefore the answer is wrong, and there are no half points. You have to get it right. And I just decided to say at lunch the other day, you know what's more interesting to me, because of course I'm a giant nerd about this, what if one of them was squared? So then we get this, don't we? And then we get a factor of times 1, which is a little tempting to miss. It's very missable because you think, well, this increased by a factor 4 and this increased by a half. There's no way that ends up back at where it started. Those proportions aren't right. But it is when you square this one. And they very much get to ask these. In fact, I'd be a little surprised if there wasn't one of these on a real test in May. At least a quick one, a multiple choice with easy numbers. Let's eliminate one of these as not changing. Here, let's do trial 1 to 2 because this does not change. Therefore, and notice when you know what you're doing, and I know I keep saying this, but you're the teacher, I know, but I hope it's a little encouraging. If you know what you're doing, not everything takes a huge amount of time. This is not going to change. Therefore, this is the source of the change for this. This grew by a factor of 2. It is the sum exponent. What's in the box? It caused a change in the rate of a factor of 2. Which one are we talking about? And this is where I mess it up, and I end up labeling it as this because I was concentrating on the wrong column in my head. This is the one we're finding the data for because it's the one that did the changing. We're finding the NO2 exponent, aren't we? So a factor of 2 increase created a factor of 2 increase. What's the exponent in the box? It is 1. Now the extra trick, and this is a little actually tricky. And of course, when they get complicated is when I like them. We now know the exponent on this. And that's how we're going to get out of the point that we can't find a way to get this to stop changing. It always changes. Okay, fine. It can't stop changing, but we know the exponent on NO. So let's pick a jump between trials where O2 changes. So we have to use 3 because it's different than 1 and 2. And then just pick honestly something. And in that other student's previous answers is probably the way I taught it. I said, why not do 1 to 3? It doesn't matter. You could do 2 to 3, but I'm not going to take the time to do it on this recording. So this changed by a factor of 4. And then how about we put that, right? Because the rate law would have NO, excuse me, it should be this. Yes, oh, that's right. That's right. Look, this changed by a factor of 4. And we just said, what exponent is on NO? 2? 1. So this changed by a factor of 4, the exponent is 1, times this changed by a factor of 2, the exponent is unknown, and it caused a rate factor change of 4. East points out, I keep saying NO2 is the product. East, you get a candy. It is NO single. I can't believe I said that. Literally, if you remind me, I will give it to you. This is the kind of dumb mistake I end up with, saying stuff like that. NO single, isn't it? Good catch. NO single increases by a factor of 4. The rate increases by a factor of 4. The exponent on this is 1. This increased by a factor of 2. The exponent is unknown. Divided by 4 gives me 2 to the power of unknown equals 2. Well, the exponent is 0. Therefore, the rate is k times NO to the first. And then O2 is the 0, so there's no point in including it. I mean, I guess you could put it to the 0 power and they would just like laugh at you and give you the point. You stated something that is immaterial. Multiplying by something to the 0 power doesn't matter. East has a question. Where did 4 times 2 come from? This here, I assume? Okay, because what we did the first time, we said the rate will change based on the factor of increase to a certain power. If the factor of increase is 1, then I can eliminate it because the factor 1, the factor of increase, to any power will not affect the rate. So when I jump from trial 1 to 2, I can eliminate this one. But technically it was there. It was a factor of 1 to some power. But I get to skip it because 1 to a power doesn't change anything. Therefore, I can say effectively a factor of 2 created a factor of 2. Then I can't get this one to stop. So what I can say is remember how they're both in the rate law and they both affect the rate? Okay, I'm going to use 1 and 3, but they're both in there. So this increased by a factor of 4, and I just discovered that the NO single, as you pointed out, factor of increase is to the power of 1. And it is multiplied by the factor of increase from O2, which is to an unknown power. And together, multiplied together, because that's how a rate law works, is the molarity times the molarity to the powers of whatever they are, create the rate. Or then you could say the factor of increase to the power times the factor of increase to the power equals the factor of increase overall. So this factor of increase is 4 to the first power times the factor of increase, which is 2 to an unknown power. Together, multiplied together overall, they created a factor of increase, which is 4. East, did I go back around enough? Oh, thank you. All right, I did. Questions are good. I'd rather solve it now than have kids lost later. So illustrating something about being a good student and also just about me, read the whole question. I'm telling you, I banged my brain on this at lunch the other day for a good 5 minutes or something before I realized I hadn't read the whole dumb question. It is a zero order reaction. Because I was trying to solve this using the first order integrated rate law and it wasn't coming out to the right answer. Duh. So this is also a little unrealistic that because the zero order integrated rate law doesn't come up on the test, they don't give it, therefore they can't ask it. So my point is not learning to use that exact law. My point is generating the numbers that even go into the law. That's where this one's useful. So what we start with is 0.2 moles of NH3. And we create, sorry, it's 0.05. That's where it doesn't work. I knew something. I was thinking, sorry, 0.05. My mistake. Bad reading again. 0.05, 0.05, 0.05. And then some kid says, it's molarity. Yeah. But you know what? First of all, they're both in a 1 liter container. So the molarity of the gas then is moles per 1 liter. So the mole number is the molarity number. The mole number is the molarity number because you're dividing by 1 liter. We have a reaction. We have 2 moles of this. We have 0.05 moles of that. But the zero order, and that's what I missed, zero order reaction, integrated rate law, go look it up, although honestly they don't ask it on the real test, so this is just an exercise in stoichiometry really. All the integrated rate laws depend on the molarity, so you cannot just take the moles and stick them in here in the zero order rate law. You have to divide by the liters. Now they made it real easy so that, and sometimes they do this on the test, that if they make the liters 1, it doesn't matter if you remembered because the number ends up the same. But technically you have to divide by the liters because this depends on the molarity and not the moles. Because the rates depend on how close the molecules are to each other and how easy it is for them to meet correctly and react. So it's not just how much you have, it's in what kind of space are you containing them. If they're in a very large space, they have very low chance of reacting. So it's the concentration that matters, not just how much you have. And just for a dumb example that leaps to mind here, I mean, if you get, if the Joker gets a hold of a can of cyanide gas and releases it at 5,000 feet over Gotham, no one dies. Because by the time it disperses to the ground, the concentration, molarity brackets, is so low that it doesn't super matter. The amount is not the point. The concentration at the end user, at where the cyanide needs to meet the cells internally in the person, just to use a horrible example, right? Matters. It's the concentration. So you cannot just use the moles. You must divide by the liters, although this time it's 1, so you get away with it even if you forget. So the NH3 molarity at the start is 0.2 over 1 is 0.2 molarity. The NH3 at the end is 0.05 over 1, which is 0.05. You know what? That is not supposed to say mole. That should say molarity. And then, because they're all in the same container, you can do molarity minus molarity. Or you know what? You could just do moles minus moles. If you wanted to say this is 0.20 moles, and that's 0.05 moles, it's going to work out the same in this case. But here's the trick. When you made one of these, didn't you use up 2 of those? So how much got used up of this? to make 0.05 moles of that, or 0.05 molarity. It doesn't super matter which way you view it. Double whatever this was. You will use double of this of whatever you just said for this. So it uses 2 times the NH3 amount. It uses 2 times of that. So it used 1 molarity or 1 mole of NH3. 1 molarity of NH3 is used. And I forgot the decimal there. And there. I was working at lunch. So 2 times that is 0.1. And because we started at 0.2 and we just decided we used 0.1, that means there is 0.1 at the end, or 0.1 molarity, 0.1 moles, or 0.1 molarity at the end. Because remember, the 0.1 moles would be over 1 liter, which would give us 0.1 molarity. So this is my starting molarity of NH3. This is my ending molarity of NH3. The zero order integrated rate law is this because I looked it up. The ending one goes first, and it is really tempting to say big minus small because you've been doing that since 2nd grade. And I have messed that up, believe me. I have to concentrate on where is the AO, and that is the starting. Times 0 at the start. Be very careful because everybody's botched that. Is 0.2. A standard, or sometimes put as AT at the time elapsed you want to talk about. If you want to put that, A sub T, at the time elapsed you want to talk about, whatever that is at the end of whatever time, it would be 0.1 equals negative KT. Oh, this also lets me discuss mental math. You can do this without a calculator. I remember thinking, isn't this one of those ones I demanded that they do without a calculator? And I was thinking, if it's here, this is supposed to be the no calculator section. So I must have demanded that they figure it out. This over that is negative 0.1. When we divide by 40 minutes, we get this equals negative K. And I kind of forget the whole process here. I'm going to try this live. I'm really figuring this out again. What did I say? I said 1/4 is 0.25, right? Oh yeah, this works. Okay. It works very much. I remember now. But I was cheating. It is not 1, it is 0.1. Therefore, my answer is 1 decimal smaller than what I just said. So 0.25, except I got to go 1 decimal smaller than what I just said because my numerator is actually 1 decimal smaller than what I was cheating with. Also, this is not 4, it is 40. It is 10 times greater. I am dividing by 10 times greater than what I said, which also pushes the decimal to the left 1 more spot. So how about I put quote marks on that? It was sort of 1/4, right? And negatives cancel out, and this number turns into that number, and the unit is per minute, and that is K. Experiment was carried out to find the kinetics of this reaction, and ln of C was plotted against time. A linear graph was produced. What does that tell us? And they think you know that when ln of reactant versus time is graphed and you get a straight line, it's a first order reaction. Oh, and I was doodling other stuff, other questions to ask actually. And I got interrupted. How does the integrated rate law? And I got interrupted. I don't even know what I was going to say. You know what we could say? This isn't where I was going probably, but again, this is not needed for the test, but you know what? We can make everybody remember it once. Here, if it's ln of a minus ln of a naught equals negative kt. I've been through it so many times, I actually remember the first integrated rate law now. Then if I spot you that, give you that, then how does it rewrite? Okay, first of all, what does this tell us? It's a first order reaction because ln of reactant versus time gave a linear graph. What do we know about the half-life? The half-life, it's constant. That's one of the defining characteristics of a first order reaction, that the half-life is unchanging. How does the integrated rate law rewrite? As Chris pointed out, you could write it like this. Or you don't even need, you know what, how about we not use brackets, because brackets in this class implies molarity, and that's already implied in the, right? So you could do effectively that. And if I add on, and maybe I'll remember, and I'll make this point, what corresponds in this to the slope of the line? What do you mean? Well, remember, if I add this over here, if I say plus this amount, I end up with this, do both sides. I end up with ln of a equals negative kt plus this moved over here, in which case, this is the slope of a line equivalent to, because it drew a straight line, didn't it? Then this equation drew a straight line. So this is y, mx, and remember this is added over, plus b. Then kids say, but these are multiplied together. How do you know which one is m and which is x? But time is something you got to choose. And how far along the graph you let this thing run is something you got to choose. So conceptually, t is x. The slope of the line is not something you just get to choose. It's inherent in the data and in like the equation. So this is m. This is the slope. So what corresponds to the slope? Negative k corresponds to the slope of the line. Because I did finally see them ask that. In fact, they asked that you use it. They asked that you find the slope of the line, which is then saying, do they know that this is y equals mx plus b, and that this is negative k is m? So when they ask you for the slope, they're saying, first you have to know that this is the slope of this is the line equation. This is the slope. You have to find k and then make it negative to get m, the slope. This is just to memorize it. A first order reaction, what are the y and x axes? ln of a and t. I think of it as first number. It's the first order. Or the first order makes me say, oh yeah, the one that kind of looks like first number. So it's ln of a, not 1 over a. 1 over a is the second order graph. Oh, this still says which of the following, because these used to be multiple choices from the guys who made the workbook. What is the likely rate law? And how do you know? Because if we look at the times going along, this molarity is half of that, and it took basically 10 seconds. This molarity is half of that, and it took basically 10 seconds. This molarity is half of that, and it took basically 10 seconds. And so if we just say, well, I mean, this is pretty good. It's pretty close to 10 seconds. It's pretty darn close. Was it zero order? Obviously not, because the amounts changing are not consistent. The molarities are getting slower. It changed 0.5, it changed 0.25, it changed 0.25. So it's not zero order. Is it second order? That is hard to spot. But you can say, well, is it first order? If it's not zero, which we just said it's not, and it's not first, then it's second because they don't ask about third or fourth. I don't even know how to spot third or fourth. And frankly, I don't even really know how to spot second. And it must be a booger because they don't ask. First of all, it's not zero, and they probably wouldn't ask that. I can't recall them asking that. Is it first? If it's not first, then it's second. So is it first? How would I know? Because the half-lives are consistent on a first order reaction. And you need to write that down. I would write that down. And they think you know it. It is not stated in any data table or reference sheet, and they think you know it. The half-lives are consistent. How long did it take for half of this to disappear? Basically in 10 seconds. How long did it take for half of that to disappear? Basically 10 seconds. And the same. So the half-life is consistent. Whoop. And so it's first order, which means the rate law will be reactant to the first power. I want to prove that you can find K using any two endpoints, right? Is there any start and any end? So just to ask, Chris, what did you start at and what did you end at?
I started at 0 seconds and I ended at 10 seconds.
Okay, so let's not do that. Let's start here and end there. And I'm doing this live, so I hope this works, but we should get, if I know what I'm doing, the same answer for K, right? K is not limited to the start and stop time. It is a function, direct function of the reaction. So if the end time, the end amount is 0.125, right? And the starting amount is 0.250 equals minus K, and the time is, though, 10 seconds, the same, right? Here's why it's going to work. Absolutely, it's going to work. You bet it's going to work, because this can be rewritten then as ln of 125 over 0.250.
Which is then equal to the natural log of 1/2.
Which is 1/2, which is what you got here, right?
Yeah.
That's my point. It works on the proportions. It's going to work for any start and any end, because in both cases, you're going to get ln of 1/2 equals negative K times 10 seconds.
And what's kind of cool is if you do the natural log of any half-life, you always get 1/2. And then if you divide by negative K, the negative times the natural log will make the whatever's on the inside become a reciprocal. So you get the natural log of 2 over K equals the half-life, which is the formula they have.
Oh, I have followed that at least. So natural log, just to prove it. Don't tell me what you got, Chris. So natural log of 1/2 And then this is going to divide under, divided by 10. And it's equal to negative k. So take the negative off. They both cancel. So is it 0.069?
Yeah, 0.069.
Oh, and then you know what? Because I have to teach a class like it means something. K has units. What will be the units? Interesting, slightly interesting question. What will be the units on K? Well, what do we need to get? We need to get rate. Rate is in molarity per time. What time are we using? Seconds? Fine. It needs to be in molarity per second. This is multiplied by that. What's the unit in here? Molarity. What do we need to get? Molarity per second. What's the unit here then? Molarity is convert into molarity per second. Therefore, the unit on K is per second. That looks like some weird character. That is supposed to be /s. There, this was all the extra stuff. So a 3% hydrogen peroxide, by the way, solution is placed in beaker A, and a 30% in beaker B, both at the same temperature. When you add this, which turns out to be a catalyst, it doesn't even matter that you know that, but they did something, whether it's a catalyst or a reactant. B proceeds noticeably faster than A. Why? You have the same reactants. Why would one go faster than the other?
Because the concentration of B is higher, so the molecules are hitting that catalyst more often.
Right. So something like the greater, this is just me talking about it. This is not the definitive all-time solution. I am taking the test, and they don't ask these deep paragraph answers, by the way, like that. But again, this is our calisthenics. I was even going to look up calisthenics because people hadn't heard that word, but I didn't. Anyway, this is the practice it harder than it needs to be to make sure that everybody gets the point. But the greater molarity of H2O2 means, and I'm just freestyling this, but something like this, we need to know this concept, even if they never ask us to write it out, because they get to ask us questions based on this concept. There are more frequent collisions with the correct orientation. And if we're pretending that this is a real question, they want a paragraph answer, which again, they don't really do on the real test, but they love including the correct orientation. I wouldn't be surprised if they didn't give you the point for this one if you don't include the correct orientation. You can't just say more frequent collisions. Again, in my pretend world where they ask this, I bet you get 0 points for that. If you skip the idea of the correct orientation that they have to hit in the correct directions to each other, kind of thing. If you have more of them hitting more often, then more of them will be more often collisions, more frequent collisions. More of them will have the correct orientation when they bump into each other. And more of those frequent collisions will have the needed threshold energy. Oh, it's 1H, isn't it? I don't think any English word has 2 H's in a row, does it? And what I mean is if you have 10 times greater the number of molecules and they're at the same temperature, that means that 10 times greater of them have energy way on the cooler end, but also 10 times as many molecules have energy way on the higher end from the average, which means that 10 times greater than the number of molecules in any one nanosecond have the required energy to react if they can just bump into the right thing with the correct orientation. You might need to hear that again. If you're on the video, replay that until it makes sense, and then ask me a question if it doesn't. And if you want to really, really, really force them to go, oh, yes, all this creates, and I'm just doing this so I can use one of their favorite phrases, more, that's supposed to be an R, effective collisions. This probably could have been said a little bit shorter if I went to the trouble of editing it and rewriting it a couple times, but I don't think they can deny me the point. The greater molarity means there are more frequent collisions because they're closer together, right? That means that since more of them are hitting per second by a factor of 10, presumably, 10 times as many of these are hitting that per second, which means 10 times as many will have the correct orientation, the correct direct hitting with the correct end. And there should be 10 times as many of them that have the needed energy to react when they hit in the correct orientation. And having both the correct orientation and the needed threshold energy is an effective collision. One more time, having the correct orientation and the needed threshold energy is what's needed for an effective collision. And if by effective collision, I mean one that will actually react. The following reaction is sped up by platinum. How can it be sped up by platinum? It's not even in the dumb reaction. It's a catalyst. And is creating a new pathway for the reaction, which is not really something they would ask probably, but it is going one tiny step beyond the scope of the test, creating a new pathway for the reaction. And here's the point that they do think you know, and they do get to ask in some way or another, that has lower activation energy. That's supposed to be a CT. Catalysts lower the activation energy is definitely one of the things that you need, that they think you know. And then we even talked about a graph where we had a potential energy. The activation energy goes in. The reaction starts happening. The energy comes out. So a catalyst does not change the starting point because nothing's even happened. And it doesn't even change the ending point. What it does, and I'm going to use a dashed line here, is it lowers the activation energy needed. And it should take less time to put in less energy, shouldn't it? So catalysts speed up reactions. How? By lowering the activation energy. 11 goes a decent bit beyond the scope of the test in a certain way, and you have to know what. I've still left it because it illustrates a point that comes up over and over in the course in general. And I guess I could replace it with something, but I don't know. You just can't do everything at once, and I haven't bothered. Okay, what you end up with butane, 4. and this is not something that comes up on the test, but one carbon uses the root of methyl, which is why it's methamphetamine, because somehow, and I have never looked it up, I guess somebody stuck another one carbon group on the side of an amphetamine molecule, which makes it methamphetamine, I guess. And somehow methamphetamine docks with the human brain better than regular amphetamines or something. Meth is not a root that means horribly addictive chemical made in shacks that makes you grind your teeth and stay awake. Okay. It means one carbon group, a carbon group that has one carbon in it. It means a group of one carbon. It's methyl, ethyl, propyl, butyl. Propane is 3 carbons. Butane is 4 carbons. So what you have is this. In case you care, this is an extension. If you want to skip ahead, go ahead. 4 carbons. And then you have as many H's as they will take. Well, every carbon wants 4 bonds, so you get just fill up the rest with H's, give it 4 bonds with as many H's as you need. This is nowhere on the test at all. They have eliminated all organic chemistry. Organic means without pesticides. Organic means carbon-based, is what it means. Technically, it means natural, but when they mean natural chemistry, they mean like life type based, which is carbon based, because on Earth anyway, all life forms are carbon based. The carbon strings are the fundamental chemistry of life. So if you look at it down the pipe, take in your imagination, swivel your head around and look down the molecule that way. Then all the H's are off to the side, huh? Then you get a viewpoint kind of like this if you ignore the ones in the middle. That's what they're doing. And my point here is this is the potential energy. These are the degrees that the H's are rotated off. None of that part will be on the test, but my point is, what's the most stable compound? Period. I don't get this part. Fine, ignore it. I don't like this. You said it's not the test. Fine. The most stable version of something is the one with the least potential energy. That's the part that keeps coming up. I would write that down. The most stable version is the one that has the least potential energy and basically has released the most energy in the reaction, or which reaction is favored, the one that releases the most energy. What does nature like to do? Release energy and create chaos. Spread things out. And I have also learned that entropy is technically not defined as chaos, and I haven't figured out why. And for the purposes of this test, it doesn't matter. So there. I would write this down. What does nature like to do? Because it's going to come up and come up. Release energy and create chaos. So the most stable version of something is the one that has the release of the most energy. And if it has released the most energy, it is the one that has the least potential energy left over at the end. This is the most stable version. And I don't know that because of the diagram. I know that because it has the least potential energy. So if we label this A, B, and C, then B has the, lowest potential energy and is the most stable. The entire point is that these can rotate this way into the paper, in and out of the paper, along these bonds here. This could be up, it could be down, because really, this is not on the test in any possible way. Really, what you get is 4. That every point is a carbon. preview of organic chem for all the super nerds who ever end up taking organic chem. There's a carbon at the ends and at the points, but they're all trying to get away from each other, all these groups, but they are attached. So they can't just let go. So the way they can get away from each other is by not being in a line, but being kinked like that. In which case you get a C up and a C down, huh? Which is this one, isn't it?
Yeah.